Here are some reminders to help you get the most out of your Dive Math CD-ROM. First, remember that God gave us mathematics to use, number one, as a tool for studying His creation, number two, as a way to interact with other people, and number three, as a way for us to learn about deductive reasoning, inductive reasoning, and analogies, which are the three main reasoning processes God has designed our minds to use. Apply what you learn about these reasoning processes to honor and glorify Him. Now, when you're doing the Dive CD lessons, make sure you work the problems with me and take notes. Or sometimes you can pause the CD and see if you can figure out a practice problem, fast forward to the answer. And if you got it right, go ahead and move on. If not, rewind and see what you did wrong. Pause and rewind as necessary until you understand a concept. That's the way to get the most use out of this CD, is make sure you understand something before you go on. Do all the problems in the problem sets at the end of each lesson, and wait to use the solutions manual after you are finished with the problem set. Make sure and show your work on all your problems, and that means being able to tell where a mistake was. If you can do that, then you know you're showing enough work. And finally, have a good attitude. The best math program in the world won't do you a bit of good if you have a poor attitude, if you don't care, if you're being lazy or complaining, or don't think that your parents should have gotten you the Dive CD or whatever. Just have confidence that your parents are doing their best for you, that God has given you this CD for a reason, and therefore you better make every second count and try to learn as much as you can while you have this opportunity. And I know God will bless you for your effort and for your perseverance for completing this course. Lesson 90 is titled Volume by Washers, and this is a deductive lesson, meaning that we'll be applying some things that we've learned in previous lessons to help us learn about this. And specifically, we'll be applying what we learned in Lesson 80 on solids of revolution to help us understand volume by washers. Think about this to start with. If you want to know the solid of revolution formed between the x-axis and then that function y equals x squared plus 3, let's say on the interval from 0 to 1 on the x-axis, that would mean this region right here revolved about the x-axis. Now, it's always a good idea to sketch out what you think that shape might look like, and I have that over to the right there. You've got those parabolic shaped edges based on that function y equals x squared plus 3. Now think about this. Let's hollow out the inside basically of that shape, and let's use this function to do it. Y equals x, just a linear function. So basically what we want to do is find out the volume of a solid revolved about the x-axis that would include this region right here that I'm shading in red. If we draw that on our solid over to the right, that means we'd have like a hollowed out middle there, and then I put dashed lines here to represent that those are hidden lines. So that's what our solid might look like now. How could we figure out the volume of that? Think about your solids of revolution formulas that you did, and just think about this. If we had a thickness here, let's call that delta x, that thickness would look like a washer. And if we knew the radius of that outside circle, we'll call that capital R, and then if we knew the radius of that inside circle, that little r, we could figure out those two cylindrical volumes, and we could call the outside one pi capital R squared times delta x. Subtract from that that inside volume, that hollowed out part, which would just be pi lowercase r squared times delta x. So with that right there, we could figure out the volume of that washer represented by that thickness delta x. So really all we're doing here is applying what we learned in Lesson 80 on solids of revolution and subtracting out a section, or hollowing out that solid of revolution with an inside section. Now think about this in the form of an integral, and we could say the volume on the integral or interval from 0 to 1 of pi capital R squared minus pi lowercase r squared, and then all of that times dx, an infinitesimally small delta x. We could factor out pi on that, and we could just say pi times the integral from 0 to 1 of capital R squared minus lowercase r squared dx. Just put all that in parentheses. Now, of course, we need capital R and lowercase r in terms of x in order to integrate this. And so for capital R at any point x, that would be equal to y, which is x squared plus 3. So let's just substitute in our two functions then for capital R and lowercase r. That's all we have to do. And so we'll have v is equal to 0 to 1 of capital R, that would be x squared plus 3. That's the capital R, so we square that value. Think about it. We're doing pi r squared. We need a pi out front of the integral too. Subtract from that the lowercase r squared, which would just be x squared. And then all of that, of course, times dx. And then let's just go ahead and solve this integral. We'll expand that x squared plus 3 squared out first, so we'll have pi from 0 to 1 of x to the 4th plus 6x squared plus 9 minus x squared. And then let's just go ahead and move this up here. We'll have pi times the integral of x to the 4th plus 5x squared plus 9. And now we can just go ahead and integrate that, and we'll end up with pi times x to the 5th over 5 plus 5x cubed over 3 plus 9x. On that interval from 0 to 1. And that would just equal pi times 1/5 plus 5/3 plus 9. And that just simplifies to 34.13. And we don't have any units that we're dealing with here, but we could just write units cubed. So what we did there to solve that, find out that volume revolved about the x-axis. It has a hollowed out middle, basically. We apply our solids of revolution relationships. Basically, you figure out the volume of a cylinder, pi capital R squared delta x, and then you hollow that out. You make a washer out of it by subtracting out that pi lowercase r squared delta x volume. Let's go ahead and do one more and revolve it with respect to the y-axis. Let's go ahead and do another one, and you can pause the CD and try to figure this one out if you want to. Find the volume if you revolved this region here from 0 to 4, this shaded region. If you revolve that about the y-axis from 0 to 4 on the y-axis, what would that volume be? The previous problem we had an integral with respect to x. This one, since it's revolved about the y-axis, it'll be an integral with respect to y, so keep that in mind. Go ahead and pause the CD and see if you can figure this one out. Like I did on the previous one, what I like to do first on these is to draw this shape, or just kind of sketch it to kind of think about. That'll help me think about what I'm doing, what it's going to look like. So what I did here is I have this solid shape that's based on the y equals 1/2 x squared if I revolve that around the y-axis. Now, if I want to just get that green shaded region and revolve that around, I need to subtract that y equals x squared. So what's going to happen is I'll have this big hollowed out section here. I'll put those dashed lines to represent that those are hidden. And so that's what my shape is going to look like. I can figure out the total volume there by just thinking about a thickness delta y. And so let's call the big outside radius, we'll call that a capital R again. And then the smaller inside one, we'll just call that a lowercase r. And so I'll have that big cylinder pi, capital R squared, delta y, subtract from that pi, lowercase r squared, delta y. And that would be the volume of that washer shape that is based on delta y thickness. Now let's think about this in terms of an integral, a sum of a bunch of infinitesimally thick washers. That's what we're doing when we figure out this volume by washer. So we'll have an integral from 0 to 4 of pi, capital R squared, dy minus pi, lowercase r squared, dy. And then we could just rearrange this to say the integral from 0 to 4, put the pi on the outside, and have capital R squared minus lowercase r squared dy. Now, we need to put a function in, substitute it in for r, the big R and the lowercase r. Think about this. Think about our outside radius based on y equals half x squared. We're going from the y-axis out to there, so that's an x distance. X is the radius. We need to have x in terms of y. So instead of y equals half x squared, we need x equals, we just solve that for x instead, and we have x equals the square root of 2y. Now, of course, that's plus or minus the square root of 2y, but we're not concerned with the minus side right now, just the plus side. And so we'll say x is square root of 2y, and then we can just rearrange the y equals x squared and say x equals the square root of y. Okay, and that's what our lowercase r is. So let's go ahead and substitute those in to our equation now, and we'll have the integral, put the pi on the outside, from 0 to 4 of big R, that's square root of 2y, that squared minus the square root of y, that's lowercase r, that value squared times dy. Okay, and then we'll simplify this, pi on the interval from 0 to 4, and that will just be 2y minus y times dy. Okay, and that'll just simplify real easily to the interval from 0 to 4 of y dy, which we can just integrate real quickly. That's going to be pi times y squared over 2 on the interval from 0 to 4. And so that would just give us 16 over 2, 8. That would be 8 pi. And we can just multiply that out. That's about 24. I'll just move it over here. 24.8 units cubed. So we don't have any dimensions on these like centimeters or meters or anything. So we'll just say units cubed because we know we're doing a volume. So we'll have something there. So volume by washers, it's basically just an application of Lesson 80 on solids of revolution, where instead of a cylinder with a thickness delta y or delta x, you have a washer, you have a hollowed out middle. And you can make a little more complex shapes now with this volume by washers method. Think about the application for such a complex geometric shape that you could make using this volume by washers method. Think if you had a computer that you programmed this into, this formula, and you wanted to have, say that you needed that shape right there for some part on an airplane or just whatever. You program your computer, which tells a robot how to build that shape exactly. Mass production of machine parts is mainly done by robots, which are controlled by a computer, which are programmed by a person who understands calculus. Okay, well that's all for lesson 90.